Okay, so let's take a look at working with roots that are not just square roots. So let's start off with kind of a review of how we reduce roots. So way back when, we looked at things like root 24, and we wanted to simplify this. So our basic method of simplifying it was we can do a prime factorization tree and split it up into its various factors. Once we'd done that, we looked through and we looked for pairs. So there's two 2's. So that means a 2 can come outside of the root. And we'd have a 2 and a 3 who don't have partners left inside. So reduced, root 24 would become 2 root 6. If we looked at root 18, we can do the same thing. We can break a prime factorization tree. So yielding thus. And again, we're looking for pairs of numbers. So we have a pair of 3's. That means a 3 can come outside. And then we have a 2 left inside. So root 18 would reduce to 3 root 2. Finally, one more. We looked at things like root 48. And again, what we're going to do is we're going to approach this from prime factorization. So I'm going to break it down. So it's a 6 and an 8, 2 and a 3, 2 and a 4, 2 and a 2. And once more, we were looking for pairs. So we have a 2 and a 2. A 2 can come out. Another 2 and another 2. Another 2 would come out. And we'd be left with the 3 behind. So that would give us a 4 root 3, 4 root 48. So this is what we kind of looked at before. Now we're going to kind of match this up and talk about other kinds of roots. So if we just have a root symbol, this is a square root. We're looking for something that when multiplied by itself gives us the number inside. But we can have other kinds of roots. And we mark that by having what type of root it is written as a teeny tiny number to the upper left. That tells us the index of the root, kind of what type it is. So as an example, this is a cubed root. Or we could have a fourth root or an n root, whatever we want to do, but we're still marking it with this teeny tiny number in the upper left portion. So let's kind of revisit what that index means when we're breaking down numbers. So if we wanted to go look at the cube root of 24, we would break it first down the same way. So just like when we had root 24, we'll still do the prime factorization. So 4 times 3, 4 times 6, 2, 2, 6 gives me a 2 and a 3. So there's my prime factorization. Before, when we had square roots, we had to bring out a pair of numbers in order for it to come out. For any other root, we need to match the index. A cubed root, this little index here, tells us how many numbers there has to be before it can come out. Since we're looking at a cubed root of 24, we need 1, 2, 3 of something before that 2 can come out. And we'd be left with a 3 behind. If we went back to our 48 as an example for a cubed root, we'd break it down. So there's my 16 times 3, 8 times 2, 4 times 2, 2 times 2. And now we're talking to cube roots. So again, we need 3 things. 1, 2, 3. A 2 would come out. We'd be left with a cubed root, and neither this 2 nor the 3 would make it out. So we'd have 2 cubed root 6. This forms our basic idea for going through and reducing roots of other indices or other power of roots. We're trying to figure out, okay, how many are there? And then we can do it that way. Now, one of our end goals for this is to realize that roots and exponents basically work as the same thing. They're considered the same thing entirely. So a root of any kind is equivalent to an exponent. It happens at the same time. The main difference is a root is a fractional exponent. So if we have something like x to the 2/3, this is when we're going to start dealing with roots. When we examine a fractional root like this, the numerator of our fraction tells us the power, and the denominator tells us the index of the root. So x to the 2/3, we look to the denominator to tell us the index. So that is a cubed root. And then the numerator tells us the power of x squared. So these are equivalent statements. They mean the same thing. X to the 2/3 is the cubed root of x squared. So we're going to be going back and forth between those two ideas to help us simplify things. So let's kind of take a look at a couple simple examples. All right, so let's say we had 16 to the 2/3 power. Okay, so again, the denominator tells us the index. This is a cubed root of 16 squared. Now, when we look at these, 16 squared, we could multiply it out. We could do our prime factorization, but that might or might not be easier to do. So this is also equivalent to the cubed root of 16 and then squared. It doesn't matter if we apply the power inside or outside when we do it. Sometimes one will be easier, sometimes the other will be easier. Just keep in mind you can do it any way you want. Same thing if we had 24 to the 3/2. All right, the half tells us the denominator is the index, so it's a square root of 24 cubed, or we could write it as the square root of 24 and then cubed. Again, it means the same thing. Use whichever one will actually work out and help you better as you try to reduce something. So let's kind of take a look at simplifying then other terms besides square roots. So how about we take a look at the cubed root of 16x to the 4th. So when we talked about exponent rules, we said that exponents go to each individual thing when we're multiplying. Same thing applies to roots. Roots are exponents. So I'm going to deal with each of these separate. So that's the cubed root of 16 and the cubed root of x to the 4th. All right, so I want to approach the cubed root of 16. I'm going to do my prime factorization. So there's my prime factorization. And again, it's a cubed root, so we need 3 of them before something can come out. So there's my 2. We have a cubed root, and there's 1, 2 left behind. Now I can deal with the x's as well. And I'm going to use basically the same exact idea. X to the 4th is equivalent to just x times x times x times x. And since we're working with a cubed root, we need 3 of them before 1x can come out. That leaves us with 1x behind, so we'd have 1x still in the root. So reduced, this root becomes 2x cubed root of 2x. All right, let's take a look at another one. How about we do the 4th root of 81 y to the 5th z to the 6th. All right, so we got more going on. Again, we're just going to break down each one individually. So I'm going to do my prime factorization of 81. That's 9 times 9, 3 times 3, 3 times 3. Then we have our prime factorization. So now we've done that, we're matching it to the fact that it's a 4th root, so we have to have 4 items before it can come out. 1, 2, 3, 4. So we'd have a 3 outside of the root with nothing left behind, nothing actually inside. Now I can look at the variables. So y to the 5th, that's the equivalent of having 5 y's in there. We need 4 of them before it can come out. 1, 2, 3, 4. We'd have a y outside and 1 y left behind inside. Finally, I could look at the z's. So that's 6 z's. And again, we need 4 before it can come out. So 1, 2, 3, 4. So 1 z can come out, and we'd have 2 z's left behind. So this would be the reduced format. 3yz, the 4th root of yz squared. So again, each time that we do this, I'm simply counting how many of them there are, and then using that to pull it out. There is another relatively quick way that you can do this, especially with the variables in particular. So let's look at our same example here. So y to the 5th, z to the 6th, all right, and we're taking a 4th root. So remember, 4th root is the same as an exponent. So that's the same thing as 81 y to the 5th, z to the 6th, all to the 1/4 power. A fractional exponent is a root. You have to be comfortable going back and forth between them. The biggest problem that people have with this unit, and this lesson in particular, is you've forgotten the exponent rules. You got them in Algebra 1, We went over them again in, I think it's 6.3 this year. So if you've forgotten your rules for exponents, go back, relook at the videos, relook at your old notes and homework for it. We have to be able to apply all those exponent rules. As an example, a 1/4 power can distribute across multiplication. So that's 81 to the 1/4, y to the 5/4, z to the 6/4. This would be another way of approaching this exact same problem. And in point of fact, this approach is very, very useful when we go to start looking at the homework. It enables us to actually apply a whole bunch of the different rules. So brush up on all those exponent rules. Make sure you remember how the bases stay the same. You add exponents, when you subtract exponents, when you multiply exponents. You have to be able to do all those still. So like I said, go back, look back over those rules if you've forgotten them. Where was I? Oh yeah, so we were looking at a way of telling what kind of root something is. So let's take a look at these two guys. If I have something like y to the 5/4 or z to the 6/4, we could break it back into roots, but there are other means of doing so. So one way is to actually look at this and think of it in terms of a mixed number. So 5/4 is 1 and 1/4. 6/4, well, we could reduce that. That's 3/2. So that's the same as z is 1 and a 1/2. That would also be another way of looking at it. Let's keep it with the 6/4 just for the moment, though. When we put that back in, that's our z of 1 and 2/4. Now that we have a matching, the whole number is the term that comes out. So we'd have a y, and then a 1/4 power is a 4th root of y. Our z, 1z what's coming out, and it's a 4th root of z squared. So if you don't like having to physically think about it this way, where you're counting out how many, canceling them out, bringing them out one piece at a time, you can also take any kind of fractional exponent and break it up into mixed numbers, and that will tell you how to break it up. I know it's a little bit confusing at first, but we'll look at a couple more examples. All right, so let's look at some examples and kind of review some of the old exponent rules. So let's say we have 108 to the 1/3 power times 4 to the 1/3 power. So just like when we talked about the exponent rules, the hardest part people have with it is there's not necessarily a right way to do it. You can manipulate this a whole bunch of different ways. We could immediately break it down and then recombine them. I find in general, it's going to be shorter and a little bit easier if we try to put everything together, especially if they're already matching exponents. So I can take this and write it as 108 times 4, all to the 1/3 power. Now that I've written it like this, now I can actually do my prime factorization on both of them. So those are 2's. 108 is a 2 and a 54, which is a 2 and a 27, 9 and a 3, 3 and a 3. So we've done a prime factorization. Now, if we can remember that that 1/3 power means a cubed root, we can go straight to that. If we can't, maybe it's better if we write it out. So that's the cubed root of our 108 times 4. So now we've broken it down and we know it's a cubed root. We know that we need to have 3 things. So there's 1, 2, 3, 3, so I'd have a 3 outside. There's 1, 2, 3, 2's, so I'd have a 2 outside. And there's 1, 2 left behind. So this reduces to 6 cubed root of 2. So that's probably the most straightforward way of approaching it. Break it all down, see what can come out, put it back into the format. We could have done it each one individually and then recombined. That would also have worked. It would take a little more steps in this case, but it would still get the job done. So let's take a look at something else. How about this? X to the 6th to the 1/4 over x to the 5th to the 1/7. All right, now this looks kind of intimidating. So let's start breaking it down piece by piece. According to our exponent rules, a power raised to another power, it multiplies. So that'd give us x to the 6/4 on top A power to a power multiplies x to the 5/7 on bottom. Next step, exponent rules. If we have the same base being divided by different powers, that means we subtract the powers. So that's a 6/4 minus 5/7. Might be easier if we reduce this a little bit. So that's 3/2 minus 5/7. Remember, you have to get a common denominator. So that'd give us 21/14 minus 10/14. 21 minus 10 is 11/14. So all of that would be equal to x to the 11/14. This is, again, just applying exponent rules to the exponents we have. Since it's a fraction, that means we can put it back in root format. The denominator tells us the index. So this is a 14th root. The numerator tells us the power of x to the 11th. And there we would have it reduced and in root format. Now we should talk about like terms. So remember, before when we talked about like terms, if we had something like x and x squared, it was not considered like terms. We could multiply them, we can divide them, but we could not add or subtract. And that's because it's different powers. Well, roots count as powers. So for something to count as a like term for us, it has to meet two criteria. One, it has to be the same index root, so the same type. If we're talking about 7th roots, everything has to be a 7th root. Second, it has to have the exact same stuff inside. We can't have different things inside the roots and still have it be considered like terms. So let's look at an example of like terms now. So how about, we'll do an easy example and then we'll do an uglier one. The square root of 3x and plus 2 square root of 3x. Okay, so to go, we check for like terms, same index root, yes. Same exact things inside, yes. So these are like terms. We have 1 something plus 2 somethings. 1 plus 2, this would be 3 of those somethings. That would be combining with like terms. So let's look at a little bit uglier example then, where maybe we're not sure if it's like terms at first. So let's look at a times 9a cubed to the 1/2 minus 2 times a to the 5th to the 1/2. Okay, so initially we look at it, we have grouping symbols, we have different powers, they're all a's, but we have different combinations, so they're not like terms when we first look at it. So we need to start simplifying. We have several things there multiplying with an exponent, so that exponent goes to all of them. So it's going to give me a times 9 to the 1/2 times a to the 3/2 minus 2 times, again, this is going to multiply, a to the 5/2. All right, well, this still isn't looking too good. Nothing really matches still. But we can do a little bit more. 9 to the 1/2. Well, maybe we can put that back in a root. So 9 to the 1/2, that's a fractional exponent, so it means a root. The bottom is the denominator, so that's just square root of 9. And that's a 3. Okay, so we can cross that guy and make it a 3. So now we have 3a times a to the 3/2 minus 2a to the 5/2. Okay, this is better. This is better. Still not good enough, though. So if something doesn't have an exponent, it has a default exponent of 1. There's one of them. Same base, multiplying. According to our exponent rules, we need to add the exponents. So 1 plus 3/2 is 5/2 minus 2a to the 5/2. Now it's the same letter. It's the exact same index root. It's the same power. These are actually like terms. We have 3 apples minus 2 apples is just 1 apple. 3 somethings minus 2 somethings, we have the 1 something left. Our final step, we would want to write it out in terms of roots. So I'll show both methods again. We could directly convert this and say, well, that's a square root of a to the fifth. Okay, so a to the fifth, that's like having 5 a's in there. And it's a square root, so anytime there's 2 a's, we can pull 1 out. And there'd be 1 a left inside, so we'd have a squared square root of a. That would be our final answer. Our other method sometimes is a lot easier at this point. So instead, I'm going to convert that improper fraction into a mixed number. So that's a to the 2.5. So there's 2 whole a's, so we have an a squared, and then we have a root. The index is a 2, so it's a square root. The power is a 1. And we end up with the exact same answer. Again, neither method is better than the other. It's just whatever will help you think it through. Okay, final thoughts for the assignment. Just a quick reminder. I do ask about some basic shapes. So for a rectangle, area of a rectangle is the length times the width. Perimeter of a rectangle is 2 times the length plus 2 times the width. For a right triangle, the area is 1/2 the base times the height. And the perimeter is just adding the 3 sides together, whatever they might be. So just remember that will help you with the word problems. For the homework, you should not be getting any decimal answers. Don't put it into the calculator. Give me a decimal. I will take points for it. Your exercise is to reduce roots as you go along. Second, your answers should be in root format. Don't leave it as a fractional exponent. All right, so hopefully this helps out. Again, the biggest reason people mess up on this is you've forgotten the exponent rules. So go back, look over all those rules from, I think it was 6.3 or from Algebra 1. So make sure that you've looked over it and reviewed it, and that should help quite a bit.